quantum computing is finally becoming practical, thanks to a groundbreaking discovery. Quantum computing has taken a giant leap forward. Scientists at the University of Sydney have unveiled a universal gate set for Gottesman-Kitaev-Preskill, GKP Qubits, a milestone that could dramatically reduce the number of physical qubits required to build functional quantum machines. By encoding logical qubits in the oscillations of a single trapped ion, researchers overcame a long-standing barrier to efficient error correction. This achievement, published in Nature Physics, https://c41567-02028, demonstrates how precise control of atomic vibrations can unlock hardware-efficient quantum logic, paving the way for scalable, fault-tolerant computation. Why fewer qubits matter? Quantum computers promise transformative applications in cryptography, chemistry, and material science. However, today's prototypes face a crippling efficiency gap. Dozens or even hundreds of physical qubits are needed to protect and operate a single logical qubit. This massive overhead makes scaling impractical. The GKP code, often dubbed the Rosetta Stone of quantum computing, offers a solution to compress logical qubits into continuous quantum oscillations. Until now, its complexity had kept it out of reach experimentally. Breakthrough in Sydney. The Sydney team utilized a single ytterbium ion held in a Paul trap at room temperature. By applying laser-driven forces, they manipulated the ion's harmonic motion to encode GKP qubits and entangle them. Crucially, their method preserved the fragile structure of the encoded states, avoiding distortions that typically undermine performance. This allowed them to demonstrate three key capabilities: high-fidelity single-qubit gates, a 2-qubit entangling gate, and the direct preparation of a GKP Bell state. Dr. Tingray Tan, a University of Sydney researcher, remarked, "Our experiments have shown the first realization of a universal logical gate set for GKP qubits. This provides a foundation to work towards large-scale quantum information processing in a highly hardware-efficient fashion." First author Vasily Matsos, a PhD student, explained that the team stored 2 logical qubits in a single trapped ion and then entangled them. To maintain stability, they used control software from Q-Control, https://qcontrol.com, a Sydney spin-off, to design optimized quantum gates that minimize distortions. Key findings: sample and setup. A single 171B+ ion in a Paul trap at room temperature. Duration. Gate operations lasted 196 to 993 microseconds. Result: universal gate set for GKP qubits plus direct GKP Bell state preparation. Efficiency: reduced physical to logical qubit ratio by encoding in ion oscillations. Fidelity: high logical fidelities achieved for single qubit and entangling gates, limited mainly by motional dephasing. Location: Quantum Control Laboratory, University of Sydney Nano Institute. Safety: conducted at room temperature, compatible with existing hardware platforms. Implications for quantum technology: these findings could accelerate the transition for lab demonstrations to practical quantum systems. GKP codes are adaptable to multiple platforms, including superconducting circuits and photonic systems, suggesting wide-ranging impact. Hardware improvements, such as faster light atom coupling and better cooling protocols, may further boost performance. The ability to prepare entangled GKP states directly from vacuum is especially promising for reducing resource overhead in future devices. Takeaway: by demonstrating that universal gates can be performed on GKP qubits encoded in a single trapped ion, University of Sydney researchers have brought error-corrected, scalable quantum computing closer to reality. Their work shows that efficient, hardware-light architectures may soon rival conventional qubit-heavy approaches. Journal: Nature Physics, DOI 1038-S41567-025-03028. https://17t.wi.ws.218. There's no paywall here. If our reporting has informed or inspired you, please consider making a donation. Every contribution, no matter the size, empowers us to continue delivering accurate, engaging, and trustworthy science and medical news. Independent journalism requires time, effort, and resources. Your support ensures we can keep uncovering the stories that matter most to you. Join us in making knowledge accessible and impactful. Thank you for standing with us.